This series of videos has been created with a view to gaining some kind of understanding or appreciation of Einstein's field equations, and we're nearly there. We're almost ready to try and justify this equation and to have some informed awareness as to what it means. In video 17 we covered this, the Ricci curvature tensor, and this, the curvature scalar. Earlier than that, from video 4 onwards, we had discussed a great deal about the metric tensor. And of course these constants should be fairly obvious. However, we've not yet looked at this, what is often called the Stress-Energy-Momentum Tensor, and we will now begin to think about that. When we spent some time reviewing the ideas of special relativity in video number 10, and therefore introduced the idea of space-time, we never really considered how that time element would affect how we should think about vectors in general. At that point in our thinking, time simply tagged along with spatial position or distance or displacement as an extra dimension. We hadn't thought much about how this three-dimensional vector had somehow become a four-dimensional vector. Furthermore, we hadn't really considered how this extra dimension of time could or should affect other three-dimensional vectors such as velocity or momentum or whatever. If you like, we didn't consider the extra dimension of time as having to be combined in any and every type of spatial vector to produce what we might call a space-time vector or four-vector instead of just a three-vector. We will now address that issue, and it will be a useful starting point for a discussion about the stress-energy-momentum tensor T mu nu. When we consider three-dimensional flat space, we often use a simple Cartesian coordinate system to measure the position of an object in that space. One convention for stipulating a point in that space was to write something like this, where m runs from 1 to 3. Inasmuch as we were simply stipulating a point in the space, we were not particularly thinking of this as a vector, but simply as coordinates for determining some position. Obviously, though, we could use this, or a similar type of convention, to describe a macroscopic three-dimensional displacement vector x, shown here in green, where x1, x2 and x3 are the contravarying components of the displacement vector. The x1, x2 and x3 could be measurements not from the origin necessarily, but from a point within the space, so that each point in space could have some kind of displacement vector associated with it, if that were appropriate. Note again that the convention being used in this diagram is a bit mixed up. Capital X in bold is meant to represent the displacement vector at the black dot, and is shown in green. Obviously, in this case, the arrow does show the extent of the vector in space. It is a displacement, after all. Throughout this series of videos, we've had the underlying issue of vector spaces, and where exactly does a vector live? We glossed over that issue, but in this case it's not a problem. The extended X here can be considered actually to be in the physical space. In terms of the components here, x1, x2, and x3 can be considered to be the contravarying component values of the vector. They are not the orange component vectors because we haven't included the basis vectors here in this diagram. However, this set of three numbers, contravarying components, could be a representation of the displacement vector x in this three-dimensional space, in the sense that xm represents the contravarying components of the vector x1, x2 and x3, or x, y and z. Now, all of what has just been said is for a displacement vector, but of course in a similar way we could represent a velocity vector v as having three components like this. This time, of course, we gloss over the idea of the velocity vector space, and we would simply stress that the velocity vector is at the black dot, and in no way does the green arrow represent any movement in the space. It is simply there to give an illustration of the size and direction of the velocity at the point. A similar kind of argument could be made for many other types of vectors in this three-dimensional space, and we could consider them as being at the point and as having contravarying components. Furthermore, as was discussed in video number 4, we can write down an expression for the dot product of a three-dimensional vector with itself. For example, if we wanted to know the dot product of a displacement vector with itself in order to find its magnitude, we said that in general, just in case the coordinates are curvilinear, we ought really to include the contravariant and the covariant components, such that the scalar product of x with itself would be written like this, which is the sum of the product of the covariant and contravariant component values. However, we realize that if we can assume that the space is flat and that Cartesian coordinates are being used, then the contravariant upper index and the covariant lower index components are identical to one another, and so the simpler and now rather unconventional formula could be used for the square of the magnitude of the vector, like this. It amounts to saying that the scalar product, or the dot product, of the three-dimensional displacement vector with itself can be written as this. Or even more straightforwardly, we'd probably write this result like this, which is clearly the square of the size of the vector displacement x. Okay, that's for situations where we have only 3 spatial dimensions. Let's now think about 4-dimensional space-time, and about the fact that we ought really to have some kind of 4-dimensional equivalent of these vectors. For instance, take the simple example of a displacement vector. As mentioned, its 4-vector would need to have the usual 3 spatial components, but also a time component. And fairly obviously, in 4-dimensional space-time, we could write the displacement 4-vector like this, again using the contravariant upper index component. We could also write the differential form of this for the components of an infinitely small displacement vector as this. Given this simple extension of what we might call 3 vectors to 4 vectors, it should seem reasonable that the rules for manipulating 4 vectors in space-time should be more or less the same as those for 3-dimensional vectors in space. The comparable formula for the magnitude of a space-time 4-vector squared would then be written with one upper and one lower like this. Or of course we could do it the other way round, like this. But once again, as we have a flat space-time and Cartesian type or Minkowski coordinates, we could write this with all upper components like this, or even more simply as this. Notice once more the negative sign for the time contribution to the magnitude, minus ct all squared. This negative sign can be said to originate from the constancy of the speed of light. We don't need to go into that detail here, but we do need to realize that the value of this 4-vector and that of the differential 4-vector does not change under a coordinate transformation. It is invariant. Now, we've met this idea before, of course, in the notion of the space-time interval squared between neighbouring events in space-time. In flat space-time, and using the Minkowski metric, this Einstein convention formula for ds squared turns out to be simply 4 terms, or more simply, this. Okay, that should make reasonable sense for a displacement 4-vector in this flat space-time and the Minkowski metric. This, or even more simply, perhaps this, is the obvious candidate for what we might call a displacement 4-vector. But what about other vectors apart from displacement? What about, for example, a 4-vector for something like velocity? If we use the letter v for velocity, what would fill the 4 positions in its 4-vector, the 4 values of the contravarying components in this case? Well, I suppose the obvious way to think about this is to start with what we've just done. Take the displacement vector and differentiate it with respect to time. That should give us velocity. But what should we use for the time component? We know that time is different for different people in relativity. We have what we sometimes call coordinate time, t, measured by someone observing an object moving, And we also have the time as measured in the frame of the moving object itself, the proper time, tau. However, providing they use the correct formula, the only one of these times that everybody agrees with and makes the same measurement of is the proper time, tau. And so that should be the obvious choice for the differentiation of the displacement 4 vector to create the velocity 4 vector. This means that the components of the 4 vector for velocity would probably best be given by this. Notice the d tau here. I'm sure you realise that this will represent the 4 contravarying components of this 4 velocity on account of the upper index here. However, according to the time dilation formula, the proper time d tau in the frame of reference of the thing that is moving is equal to the coordinate time dt in the rest frame of the other observer divided by gamma, the Lorentz factor. This means that in terms of t, the outsider's coordinate time, the velocity 4 vector would be given by this expression. So we now seem to be using what you might at first think is the wrong time in the equation, one which is different for different observers. But of course the gamma is in the formula and that corrects for that and gives an overall value which everyone agrees with, the proper time. The 4 measured components then of the velocity 4 vector could be written as this, which is also this. Or if you like, we could show the 4 components of the 4 vector like this. Notice though that this first derivative here, dt by dt, is equal to 1. And so the time component here is simply c. Also, the rest of the components here are clearly seen to be the velocities as measured in the coordinate frame of reference. Notice the t on the bottom. This means that the velocity 4 vector, or rather its contravarying components, can now be written like this. And this expression should probably seem reasonable for what we might call the velocity 4 vector. These 3 spatial components are simply the coordinate measurements of the velocity, amended of course by the Lorentz factor outside the bracket, which is what you'd expect in relativity. This time component is the velocity of light. What else could it be? Again, of course, it's modified by the Lorentz factor. However, what might be surprising for some people comes when we begin to think about a 4 vector for momentum. We can define this simply by multiplying this velocity 4 vector by the rest mass of what's moving, m0. This would give, for the contravarying components of the 4 momentum, this. And multiplying each component by m0 would give this. And doing the same with the gamma, finally, is this. So these are quite logically the 4 components of 4 momentum in 4-dimensional space-time. Now in some ways, I suppose, these 3 are also fairly easy to interpret. Gamma m0 is the relativistic mass, which will be close to m0 when velocities are small, and when multiplied by the components v1 to v3, this mass will give the spatial components of momentum. That's fine. But what is this? The time component of this 4 momentum. How do we interpret this term? Well, you should recall from what you have hopefully already done in special relativity that the total energy of a particle is given by E equals mc squared, or gamma m naught c squared. And if you remember, one of the teaching exercises that's always done with this formula is to expand this gamma here and then show that at velocities well below the speed of light, this formula approximates to the rest mass energy plus Newtonian kinetic energy. Well, another thing that you can do with this formula is to divide both sides by the speed of light, c. But this can be seen to be the time component of the momentum 4 vector. In other words, the total energy E of the particle divided by the speed of light, c, is the time component of the momentum 4 vector. And that means that the momentum 4 vector, or the contravarying component of it, can be written like this. So it seems that we started off here wanting the 4 vector for momentum, and we've found that the new time component of it is actually to do with energy. Now, we won't go into any more of the mathematics of all this, and we don't really need to look into any other types of 4 vectors, though there are many. These two, the one that relates to time and space, and the one that relates to energy and momentum, will probably be enough as far as our discussion of general relativity is concerned. There's one very important thing to notice about each of them, however. If you calculate the sum of the squares of the 4 components, making the time element negative, you get an answer which is invariant. In other words, an answer which all observers in any inertial frame will agree on if they do the same calculation with their measurements. We already know, for example, that this is true for the space-time 4-vector x mu, because the calculated length of this is the same in all inertial frames of reference, and we could probably write the square of this for flat spacetime and Cartesian-type coordinates something like this, where we know that the Minkowski metric has brought in a negative sign for the time component. And this kind of calculation could be done with the square of the energy-momentum 4-vector, and would go along the similar lines. If we calculate the sum of the squares of the 4 components of energy-momentum, we get this, the rest mass squared multiplied by c squared, or the rest mass times the rest energy. And of course this is something which is invariant. The rest mass doesn't change and the rest energy doesn't change. Now, a rigorous derivation of this would go along these lines using the Minkowski metric to bring in a negative sign, but hopefully you get the picture, namely that the square of the 4 momentum is something which, when measured in any frame of reference, would give the same answer. It is invariant. This kind of thing was apparently such a striking result to Einstein that he is said to have considered calling his special theory of relativity a theory of invariances, or a theory of absolutes. Certain things, like the size of a space-time vector or the size of an energy-momentum vector, always give the same answer in inertial frames regardless of the velocity of that frame of reference. Now, going back to the energy-momentum 4-vector, it probably shouldn't really surprise you that we've just found that the time component of momentum relates to energy. From special relativity studies, you may recall that the connection between energy and momentum is given by this formula, where m0 is the rest mass and p squared here is the square of the size of the momentum and not the component p2. In fact, this p squared represents the sum of the squares of the spatial momentum components, if you can see through the ambiguity in this way of writing it here. You should also recall that the energy of a particle can be written as the rest energy, m0 c squared, multiplied by gamma, the Lorentz factor, and that each component of the momentum in the x, y and z directions can be shown from special relativity to be the Newtonian momentum, mass times velocity, multiplied by the Lorentz factor, gamma. This means that we have a number of ways of writing down the momentum 4-vector, or what is actually called the energy-momentum 4-vector. Here are just 2 of them. Notice that in the second of these expressions there is a certain obvious consistency. Each of the entries looks like a kind of momentum. For our purposes, we don't really need to go through all the equations that will link one thing to another for this, but simply to realize that 4 vectors like this are invariant to coordinate changes between inertial frames. Okay, so having looked at a couple of 4 vectors in Minkowski spacetime, such that the rules of special relativity apply, and in particular having looked at the energy-momentum 4-vector, which can be used to describe the energy and momentum of a single particle travelling through spacetime, we want now to consider how we might describe a region of spacetime which has some sort of mass energy distributed throughout it. When we were discussing Newtonian gravity in 3 spatial dimensions, not spacetime, in earlier videos, we generally thought in terms of discrete masses, planets or whatever. A slightly more complex situation would have been to think in terms of the particles making up the mass being spread throughout the region of the space. In that kind of non-relativistic situation, we would have been thinking in terms of mass being distributed throughout the space, such that at each point in that space there was what we might call a mass per unit volume, or mass density rho. However, it ought to be obvious that even in special relativity, it's not enough only to talk about the density of mass, rho, at every point in space, or rather at every event in space-time. For one thing, we're now used to thinking in terms of mass being energy, and vice versa. But on top of that, the mass might be moving, or there might be electric and magnetic fields present, and the like, and that means even more energy. Clearly something else is needed in order to describe even the distribution of what we might call mass energy throughout space or space-time. And as we move towards thinking about general relativity, whatever that thing is, it will be the thing that will be said to distort space-time. Anything that has any kind of mass or energy. Simply using the mass density rho will not be enough. And judging from our discussion of space and space-time so far, and the importance of things like the metric tensor and the Ricci curvature tensor, each of which were rank 2 tensors, it seems likely that we are going to need an extra tensor with 2 indices, which will describe the mass-energy distribution in space-time. That will mean that we will then have 16 measures that we can use to represent this so-called mass energy at every event in spacetime, not just one measure of mass density rho. The following discussion therefore will explore what such a tensor might look like. It will be called the Stress-Energy-Momentum Tensor, or sometimes simply the Energy-Momentum Tensor, or even the Stress-Energy Tensor. The tensor will be written like this in covariant form. Once again, this is difficult to explain rigorously without going through some very arduous mathematics, but we will try to give meaning to parts of it, and to some extent at least justify the need for using something of this form in Einstein's field equations, rather than the more basic mass density rho. As mentioned, the stress-energy-momentum tensor is shown here with covariant or lower indices, but it could equally well be written and used in its contravariant form with upper indices, or with a mixture of upper and lower. You should recall why this is so. It is, in principle at least, quite easy to convert one form to another using the metric tensor either once or twice. Here are the formulae, for example, to change both indices from up to down, and also from down to up. Again, as a quick reminder about this kind of conversion, looking at the first of these formulae, which shows how to change the contravariant form to the covariant form, it should be obvious by now that each of the 16 new covariant components will actually be a complicated mixture of all 16 of the old contravariant components, and also parts of the metric tensor. For example, here is what T00 lower looks like, this is the one in the top left-hand corner, as a function of all the upper components when considering four-dimensional space-time. Do that 16 times, evaluate the numbers, and you will have changed the doubly contravariant stress-energy-momentum tensor with upper indices into the equivalent doubly covariant stress-energy tensor with lower indices. Now, I mention all that about changing uppers or lowers and the like because it's actually a little bit easier to try and explain what things are and why they are what they are by using the doubly contravariant form with upper indices like this. And yet, we are going to need the doubly covariant form when we fit it into the field equations in the way that we will formulate them. So bear that in mind. We will eventually flip from talking about one type of thing to the other. Let's start by thinking a little bit about the energy-momentum 4 vector. Let's face it, energy is going to be the important thing. Energy, mass, mass, energy. So the 4 vector for energy momentum is a good starting point. As we saw a moment ago, the idea for the energy momentum full vector of an object came from the formulae of special relativity, and it could be written like this, which is really the expression for the contravariant upper component of the full vector. It has a time component, which is like energy, and 3 spatial components for the relativistic momentum. We also saw that it could be written like this, or even this. P0 is the time component of this energy momentum full vector and represents energy, or rather mass energy, whereas these are the 3 spatial components and represents relativistic momentum in the 3 directions of space, x1, x2 and x3, or x, y and z. We're thinking about 4-dimensional space-time here, but for the moment let's consider a small physical volume in the 3-dimensional space of it, namely dx, dy, dz, or rather dx1, dx2, dx3. Here it is marked out by these dotted lines, and it's supposed to be infinitesimally small. Consider that in this small volume of space there is energy and momentum, and that could come from all sorts of things. It could be from mass that's there, spread throughout the volume, and of course the mass could be moving as well, and so there would be kinetic energy, or there may be energy from other things that are there, electric and magnetic fields, photons or whatever. If we now consider there to be a small amount of energy momentum in this infinitesimally small region, not fields or photons, and it's given by this 4 vector, and suppose we somehow divide this 4 vector by the volume itself, dx1, dx2, dx3, and then let the volume tend to 0, we will get a 4 vector for that point in space and time, which we could represent like this. Now look at this and make sure you're happy with it. It is the triple differential of the energy momentum 4 vector, and of course partial differentials have had to be used. This component of this 4 vector effectively tells us the mass energy per unit volume at the place, and these are the various components of momentum per unit volume at the point in the x1, x2 and x3 directions. Now we will need to think about what we might mean by momentum per unit volume, but it should be fairly obvious what this part of the particular 4 vector means. For example, if all we had at the point was an amount of ordinary mass, which we might call relativistic mass, and it was at rest, then this first component of this 4 vector would simply be the mass density rho at that point. This term, the energy per unit volume, would essentially be the mass per unit volume rho multiplied by c squared. If we didn't have mass there, but perhaps we had an electromagnetic field in that region, then this first component, the mass energy per unit volume term, would be something probably more like this, where E and B are the electric and magnetic fields at the point. Of course, if there were multiple sources of mass energy at this point, then this first component could be quite complicated looking. Now, sticking with mass type energy for the moment, moving or otherwise, here's where we take quite a big step forward to think about the Stress-Energy-Momentum Tensor, which we're going to need for general relativity. These 4 things, this energy momentum density 4 vector, can be considered to be the top row of the Stress-Energy-Momentum Tensor, the version with contravariant components. T00 is the mass energy per unit volume at the point. Remember, P0 is E over c, energy over the speed of light, and it's divided here by the volume of the box, dx1, dx2, dx3. The next component, T01, on the other hand, is the momentum per unit volume in the x1 direction at the point, and so on for the other 2 spatial directions, x2 and x3. Okay, before we move on, can we make sense of the 2 indices that these 4 top row components have, 0, 0, 0, 1, 0, 2 and 0, 3? Well, the second index for each of them, 0, 1, 2, 3, obviously relates to the components of the energy momentum being used to calculate it, 0, 1, 2, 3. But what about the first index, all zero for this row. Why is that? Is there a significance to it? Well, a simplistic answer would be to say that these first zeros relate to the direction that was not used in forming the density. What do I mean? Well, we essentially divided each of these by dx1, dx2, dx3, but we did not divide by dx0. Why would we? That's obvious. But in a way, that could be said to be the reason for the zero in the first index of each of these components on the top row, as will hopefully be made clear in a moment. Before we do that, let me illustrate the mass energy density term and the momentum density terms on this row a little more clearly and give them different highlighted colours to help distinguish between them. The first, shown here in purple, is the mass energy per unit volume at the point, from its rest mass and from any movement. And the other three, in yellow, are the components of the momentum per unit volume in the three directions, x1, x2 and x3. I hope that makes reasonable sense so far. Now let's take a look at the other three rows of this tensor. What on earth do they mean? Well, if the first row was formed by a derivative that didn't involve x0, that didn't involve time, we can now include x0 in the derivatives for the other rows, but take away x1 from the derivative of the first row, take away x2 from the second row, and take away x3 from the bottom row, still keeping three things in our derivatives that form the components of the tensor. In other words, we'll always divide by three things, or rather take the differential with respect to three things. But the fourth thing that we will miss out each time will relate to the number for the row that we're on. Hopefully you'll see what I mean in a minute, especially when we start to think about flux. Thinking then about the second row of the tensor, if we again take the derivative of the energy momentum 4 vector, but this time with respect to x0, x2 and x3, missing out x1, we would get the following differential 4 vector for the second row. Notice that in many ways we're still differentiating with respect to a volume. In relativity, time is treated very much like a distance and can have units of distance. What's missing in this row is x1. Let's focus for the moment on the mass energy part of this first component which comes from the differentiation of P0. How can we interpret this term? Well, you can see here I have put the time part in red. Well, for this particular event in space-time, it is the rate of change of mass energy, that's P0, per unit area per unit time. But what area? Well, the area made up of dx2, dx3, which is the area facing the x1 direction, the very thing that we missed out in the differentiation in this row. It may help to look again at the diagram showing the small physical volume dx1, dx2, dx3 within the three-dimensional space. This term that we're looking at here, d3p0 by dx0, dx2, dx3, can also be written like this, d by dt of d2p0 by dx2, dx3, where the differential with respect to time has been taken out. This can now be seen to be the rate of change of mass energy per unit area per unit time, flowing in the x1 direction. Remember, the area dx2, dx3 faces the x1 direction. And it's saying that if more comes out than goes into this area, as indicated by these two red arrows, then this term will be positive. Now you will know that the flow of something through an area per unit time constitutes a kind of current, and the value of that current is defined as the amount of that thing passing through per unit area per unit time. If we therefore consider this small space-time volume to be shrunk to zero, that means that here dx0, dx2 and dx3 will shrink to zero, so that this term will represent what we might call the sum total of the current of mass energy coming out of or going into the point in the positive x1 direction. If this term is positive, then mass energy is coming from the point in the x1 direction. If it's negative, then there must be a resultant current of mass energy going into the point in the x1 direction. Notice here we're talking about the x1 direction, the very direction not used in the differentiation on this row of the tensor. So with a fair degree of logic, we can identify this term, the first one in the second row of the stress-energy tensor, as being the energy flux through the point in the x1 direction. More explicitly, it is the energy per unit area per unit time leaving the point in the x1 direction, and the indices of the tensor component, 1, 0, agree with the pattern that we suggested before. 0 for the fact that we're talking about energy, the zeroth component of the original 4 vector, and 1 for the fact that the energy flux represented by this component is in the x1 direction, the number not used in the denominator of the differentiation. Now I know we haven't said what these are yet, and they were part of the derivative for this row, but let me move on to the next row so that I can discuss this column for the moment, and we'll get to all the rest in a minute. If we did the same kind of thing for the next row down, the third row, and took the differentiation of the energy momentum 4 vector with respect to x0, x1 and x3, missing out x2 this time, we would get this. Notice that there's no dx2 now in the differentials. It should be obvious from what we just discussed from the other row that the first term here represents the energy flux coming from the point in the x2 direction through the area made up of dx1 and dx3. If it's positive, there's more coming out than going in, and vice versa. And so we can add that here. Finally, for this left-hand column, it should now be obvious that the bottom term represents this situation. And we can therefore identify the T30 as the flux in the x3 direction, representing a differential that involves x1 and x2, but misses out x3. These three terms, highlighted now in green, could be called the energy flux. They all relate to the energy, P0, as shown in their second index, and they give the energy per unit area, per unit time, leaving the point in the x1, x2 and x3 directions. When I say the point, you should recall that each point or event in space-time has these 16 numbers of the stress-energy-momentum tensor associated with it, and each event in space-time will probably have different values of those 16 numbers. These three green numbers relate to the energy per unit area per unit time leaving the point in the x1, x2 and x3 directions. Now, before we get to thinking about these components and what they might mean, there's something interesting about the three energy fluxes highlighted in green that we've just been looking at. It can be shown that this whole stress-energy tensor is symmetric. Now, we won't attempt to prove that mathematically, but if you accept that fact, then the consequence is that these three greens in the first column are individually equal to these three yellows in the first row. Take the first one as an example. This would mean that T10 is equal to T01, or this green differential equals this yellow one. Now, if you look at this, it might seem at first to be hard to swallow. This contains energy, P0, whereas this has a component of momentum, P1. This is a derivative with respect to time and space, whereas this is a derivative only of space with no mention of time. However, they can be shown to be identical from the mathematics. At a simplistic level, the right-hand side here does have a rate of change with respect to time embedded in it, in the idea of the momentum or the velocity. There is the rate of change of displacement with time, so the apparent absence of time on the right-hand side should not be an issue. Anyway, you can look into the rigorous mathematical proof of it, or if you wish, The point here is that this whole energy-momentum tensor is symmetric, and so we can illustrate what we've done so far not so much like this, but like this, using the same colour for each. Let me talk through these two components as an example. They are equal to one another, but in explaining things via the indices they can sound very different. For example, in T20, this 0 means energy. Everything in the first column is about energy, and the 2 here is about the direction of the energy flux that this term measures. On the other hand, we've suggested that this 0 in T02 is about movement through time. It's really from the fact that time was not involved in taking the derivative to create this term. It was a straightforward density measure, wholly spatial, and its movement, if I can use that word, is through time only, and this 2 is the direction of the changing momentum which this term represents at the point. We have two very different ways of thinking about these terms, and yet they are essentially the same as one another. They will have exactly the same value as one another. As I say, look up the proof if you want. Okay, the next thing we ought to do is to think about all the remaining terms in the stress-energy tensor, those shown here for the moment in light blue. If you recall, the whole of this tensor could be represented by derivatives like this, where they've been coloured to match the scheme we have at this stage. Each entry here is a derivative with respect to 3 of the 4 dimensions of space-time. And taking our cue from the 3 yellow components in the first column that we've just talked about, which were about energy flux in the 3 directions, the light blue ones could all probably therefore be interpreted as momentum flux. We have 3 directions of momentum, and we have 3 directions in which momentum can change via flux, and that means we have 9 terms altogether. As to what the phrase momentum flux actually means, well, that's another matter. Let's think about it as best we can. Take, for example, this component, which is the T12 component. 1 from the rho, the number not used in the differential division, and 2 for the momentum component. If we once again take the time differentiation out and write it like this, we can simplistically interpret this as a kind of flux through the area x2, x3, in other words, in the x1 direction. But it is a flux of the momentum in the x2 direction. It's the change in P2 through the area dx2, dx3 with time. Here's an attempt to picture that before the volume and time are made smaller and smaller and approach 0. The P2 component of the momentum is shown in blue, and the rate at which it changes in the x1 direction is shown here in red, all taking place at a point, of course, when the volume shrinks to 0. So if this T12 component is positive, then at the point it means that more P2 momentum component is leaving the point via the x1 direction than is entering it. The P2 component would then be diminishing in that direction. Note that this only deals with changes of P2 in the x1 direction. What's happening to P2 as far as the other directions are concerned will depend on the other components. Now, I don't think anyone would suggest that this is an easy concept to grasp. However, the second way in which these light blue components can be interpreted is perhaps a little easier. They are, in fact, measures of stress or pressure, and you can see that by thinking about the likely units used to measure them. These 9 light blue components of the tensor are calculated from momentum divided by time and also divided by area. The units of momentum divided by those of time give the units of force, so altogether we have for them the units of force divided by area, which are the units of pressure or stress. It's worth remembering at this point, however, that there are actually 2 types of stress. What you might call ordinary stress can be thought of as being similar to pressure, and is calculated by dividing the force by area, where the force is acting perpendicular to the surface of the area, or rather in the direction of the area vector. However, there's another kind of stress, the shear stress, and this is calculated by dividing the force acting parallel or along the surface by that area. And I suppose we should say that in that case the force is perpendicular to the area vector. As you will see in a moment, 6 of these 9 tensor components highlighted here in light blue relate to some kind of shear stress at the point. And so not only can we call them momentum flux, which we've just talked about, but also we could call them shear stress. However, as we said, on account of the symmetry of the stress-energy tensor, these 2 sets of the 3 components shown here in light blue are respectively equal to one another. And so, on account of the fact that we have 2 ways of naming them, we could label one of the sets of 3 as momentum flux and the other as shear stress, like this. Now, in order to see why the label shear stress is appropriate for these components, let's look again at the component T12. The diagram we had a moment ago for this showed the momentum flux interpretation. And in that interpretation, we first took the expression for the derivative which produced that component, and then we took the time derivative outside and thought about it in this way. This interpretation, if you recall, gave us the rate of change of the momentum flux with time. However, we could equally well think of the derivative term like this, taking the spatial derivatives outside. This is exactly the same thing, but here we can see that this is a force. It is the rate of change of momentum P2 with time. And it is divided then by the area facing the x1 direction, in the sense that this double derivative outside then takes what we might call the area derivative of that force. And the force over area is a pressure or stress. However, the force is along that surface dx2, dx3 in a shear kind of way. It's not normal to the area surface. It's not a pressure in the conventional sense. It is what we call a shear stress. The force acts along the infinitesimally small surface. So, we can think of each of these 6 components in 2 ways. We have a shear stress, if we think of it that way, or we have a momentum flux, if we think of it in terms of the momentum per unit area divided by time. And it's usual, therefore, to label one set of 3 momentum flux and the other set of 3 shear stress. But I suppose these light blue labels could be swapped over, as they essentially mean the same thing. Finally, what about the 3 diagonal components shown here now in grey? We know they could be thought of as a momentum flux, but what about some kind of pressure or stress? Well, if you think about it, these 3 diagonal components are a little bit different from the rest of the 9 in the centre here. These have the momentum direction perpendicular to the surface through which the flux passes. In other words, pointing into it directly in the direction of the area vector. Take, for example, T11, which is given by this formula, or if you like, this. You can see that the momentum direction, P1, and therefore the force we get from taking the time derivative of it, is in the x1 direction. But the surface of the area, dx2, dx3, is perpendicular to the x1 direction, or if you like, the area vector is parallel to it. And so we have this kind of situation. It's a pressure or stress, not a shear stress, but an ordinary kind of pressure. Well, I say ordinary, but clearly it's not like our everyday idea of pressure. Usually in ordinary situations, the pressure at a point has no direction. It's not a vector, and in a way, it's the same in all directions. At least that's what we say in high school physics. Here, however, the pressure from the changing momentum at a point in space-time can be different in different directions, depending on the values of the forces at that point, because these in turn are the time derivatives of the 3 momentum components at the point. So, there we have it, a 2-index tensor T mu nu, which we call amongst other shorter forms the Stress-Energy-Momentum Tensor, and which instead of rho, simply for mass density or rho c squared, can be used to represent all kinds of mass energy at different points in space, or should I say space-time. All parts of this tensor can contribute to the curving of space-time. The presence of mass, the movement of mass in terms of kinetic energy, and also the movement of mass in terms of a kind of pressure or stress within space-time. And of course, that's putting it rather simplistically. This tensor is a relativistic beast. On the other hand, for many situations, the T00 term will be the dominant one. Unless velocity is exceedingly high, T00, which can be thought of as rho c squared, will be the main contributor to the curving of space-time, all the other components of the tensor being effectively zero. This is, as you might expect, on account of the exceedingly high velocity of light, which makes any reasonable mass contribute a large amount of energy, compared to situations where kinetic energies in the light would be much smaller. Now we will, as mentioned earlier, from now on tend to use this tensor in the form which has two lower or covariant indices, and we know how to change the version shown here into the doubly covariant form by using the metric tensor, which would then give us this. Hopefully at this point we now have at least some understanding of the stress-energy-momentum tensor. However, before we can start to think about Einstein's field equations, there's one other thing that we will need for that discussion, and that is the continuity equation for mass energy. On the assumption that mass energy must be conserved, let's see how that concept applies to the components of the stress-energy-momentum tensor. Let us first focus on the energy aspect of things in the first column, what we've called the mass energy density at a point, and three components of the energy flux through that point. We'll consider first T00, which represents the mass energy density at a point in space at a particular time. There's no mention of time in the way it's been calculated, it's just mass energy per unit volume of space, but it is obviously dependent on time as well as on position. In fact, we could write T00 as a function of the four components of space-time, like this. If we were therefore to calculate or write down the rate of change of this component with respect to time, it would of course be this. And this would represent the rate at which the mass energy density at the point changes with time. If you prefer to think in terms of an infinitesimally small box before the volume tends to zero, it would be the time rate of change of mass energy per unit volume into the small box shown, a measure of a sense in which it is increasing with time. If this term, dt00 by dx0, is positive, then the mass energy density at the point is increasing with time at the point. If negative, it is decreasing. If it is increasing, then that means there must be an overall influx of mass energy coming in from either the x1, x2, or x3 directions, or some mixture of them all as time goes on. Now remember that these three flux terms in this first column, T10, T20 and T30, each represent the mass energy per unit area per unit time in the three directions. If one is positive, it means that mass energy is leaving the point via that direction or that face of the box. In order to find the total rate at which mass energy is leaving the box, we would need to differentiate each of these terms by their respective distance direction. This would then convert the flux measurement of mass energy per unit area per unit time into a volume measurement of mass energy per unit volume per unit time, and the total mass energy density leaving the point, or box per second, would then be given by the sum of these three terms for the three directions. Now if you think about it, this should have the same value as the expression we obtained from the top component in this column, The derivative of that top component with respect to time gave us an expression for the rate of increase of mass energy density at the point, and it was dt00 by dx0. And so these two expressions must be equal in size, though one is the negative of the other. In other words, we can write this. Rearranging to put everything on the left gives us this. And this equation could be called the continuity equation for the mass energy. It crudely says that what goes into a point in terms of the flux from various directions must equal the overall increase in the mass energy density at the point, and vice versa. It may look strange to some in that this is a derivative with respect to time, whereas these are with respect to distance. But don't forget, this has an extra distance in it from working with the volume, and these have an extra time in them from working with the momentum. Anyway, it all makes sense if you think about it. The mathematics takes care of it all. This equation, of course, applies only to the first column of our stress-energy tensor. However, if you think about it, each of the other three columns must have exactly the same kind of relationship between their entries. It's just that they are dealing with momentum flux in the three separate directions of space rather than with energy flux. We can say, therefore, that we have four equations for four-dimensional space-time which describe the continuity of the stress-energy tensor, one for energy and three for momentum. Now, it should be possible to think about working backwards from these four equations to the Einstein summation convention version of things, and if you think about it long enough, you should see that these four equations can be written like this. Four equations, that's from the nu index, and each equation has four terms, that's from the sum over the mu index. So we now not only have some understanding of the stress-energy-momentum tensor, hopefully, what it's made of and what the terms or components in it mean, but also we should now have some sense of the way in which the various parts of this tensor are interconnected via the continuity equation, or I should say equations. Finally, however, and very importantly, when dealing with general relativity, the likelihood is that curvilinear coordinates will be needed, and that means that the ordinary derivative is not good enough. We need to be using the covariant derivative, because if there is curvature, then the covariant derivative will take into account the various distortions that are in the metric tensor so that measurements remain invariant. This means that the continuity equation for the stress-energy-momentum tensor should, from now on, be written like this: capital dt mu nu by capital dx mu equals 0, which in the four dimensions of space-time means these four equations. Here, the tensor components have been highlighted to match our explanation of them. And that's it for now. We will use this continuity equation in a very simple way when we discuss Einstein's field equations, which, instead of a simple rho for mass density, will contain the stress-energy-momentum tensor, and that whole discussion is not far away. If, however, you need a reminder at this point, the covariant derivative of vector components is given by this for contravariant upper components, and by this for covariant components, where you can see again that the difference between these two equations is simply a plus or minus sign for the correction or the connection term. The Christoffel terms, the gammas here, are given by this. Of course, these covariant derivatives here have been written out using vectors, or what we would call rank 1 tensors, but we've shown previously how they can also be applied to tensors of higher rank, and so it shouldn't be difficult for us to see how the covariant derivative of a rank 2 tensor, such as the stress-energy-momentum tensor, can be taken. Okay, so we now have all the information we should need in order to consider how Einstein's field equations could be put together from scratch, or at least from what we know. In the next video we will attempt to do just that, to look back at some formula from Newton's gravitation and then using all the ideas we've discussed so far to manipulate them into the field equations of Einstein. Whilst it won't be a wholly rigorous exercise, it will basically follow Einstein's thinking and should give us an understanding of what these equations are getting at. This video has discussed the stress-energy-momentum tensor. We now have everything we need to be brought together to form Einstein's field equations, and in the next video, number 19, we will do just that.